We will also with the exercise sheet, depending on how far we get. I might do a little bit of lecture too. Okay, so welcome back to the EFT lecture. Today we will finish our chapter on renormalization, and to quickly finish it, I would like to highlight 3 further points with the title Properties of Counterterms and Renormalization Schemes. Namely, I would like to tell you a little bit more details on the bare Lagrangian and how it can look like. We will see that it can be obtained by, let's say, a recipe called renormalization transformation. And we will also see under what conditions such a renormalization transformation actually works. Then we will discuss a little bit more renormalization conditions, or equivalently renormalization schemes, such as on-shell scheme versus MS-bar scheme and so on. And finally, we discuss also renormalization scheme changes and the 3 parameters of the theory. We alluded to this already last time. Okay, so let us begin with the bare Lagrangian in general. And remember, the whole discussion is basically a blueprint. Examples will form the rest of the semester, but here I summarize basically general statements which are always valid. And so in general, we know about the bare Lagrangian only what comes out of the theorems that we discussed the last time. And the theorems tell us that there always exists a bare Lagrangian which makes the theory finite, and what we know about it is that it is a local relativistic Hermitian Lagrangian. That's all. Therefore, in general, we know that it can be written as a sum with coefficients, let's call them Ci bare, times operators Oi, where these are coefficients. And these are local Hermitian relativistic operators. And operators mean that these are constructions out of the field operators and derivatives of the theory. Obviously,
طبعا هنا في شيء مهم، وهو أن الكوفيشنت، يعني كوفيشنت يمكن نقول أنها تخبرنا ما يسمى بالدايفيرجنس، وتخبرنا أيضا الفيكس هنا بيحصل الدايفيرجنس. لكن ما يهمنا هو الأوبريتور. هذا الأوبريتور فيه شيء غريب. هذا الأوبريتور يحتوي على الجزئين، الصراع يعني البسط والمقام، الكتلة أو الطاقة والمقام الفضاء ثنائي الأبعاد. لماذا قلت هذا الكلام؟ لشيء بسيط، ما ذكره البروفيسور عن الهرميشن. الهرميشن في نظريتي، يعني يذهب إلى سلسلة الشيطان أقبح في التفاصيل. كلمة هرميشن هناك، يعني هناك داينامكس، وهناك حركة بين الكتلة والفضاء. لا يكون الأوبريتور هرميشن إلا إذا كان هذا الأوبريتور أثر في الفضاء ثنائي الأبعاد، بحيث أن الفضاء ثنائي الأبعاد يجعله هرميشن، بحيث أنه يبدد الطاقة التي فيه. بالتالي نجد أن ما يسبب الأوبريتور يسبب الدايجونالايز دائما للماتريكس بالنسبة للفيلد. الأوبريتور يعمل الدايجونالايز دائما، بما أنه يعمل الدايجونالايز وبالتالي يعني أنه يسبب يؤثر في الفضاء ثنائي الأبعاد، والفضاء ثنائي الأبعاد يؤثر فيه، وهذا التأثير المتبادل هو السبب الذي يعمل الدايجونالايز. إذن من هنا يمكن أن نحدد أن الأوبريتور ذات نفسه لابد أن يحتوي على هذا الصراع بين الفضاء ثنائي الأبعاد والكتلة. بعد ذلك يأتي الكوفيشنت، والكوفيشنت هو الذي يجعل اللاجرانج فنايت، وبالتالي فنايت يعني محدود، وبالتالي هذا الكوفيشنت لابد له أن يحتوي على الكوبلينج كونستانت، وأيضا يحتوي على الرينورماليزيشن على ما أظن، وهكذا. لكن الأوبريتور ذات نفسه هو الذي يحتوي على هذا الصراع بين الفضاء ثنائي الأبعاد والكتلة. طيب هذا طبعا تنبؤ، تعال نتأكد من صحة هذه المعلومة.
The set of all local Hermitian relativistic operators forms a vector space, and therefore you can here choose a basis in this vector space, and the statement can be written as saying that the bare Lagrangian is just some linear combination of the operators in this vector space. So let's say we can choose a basis. And only if you choose a basis, the values of the coefficients are obviously unique. But there always exists such a construction of the bare Lagrangian. Okay, now there can be two further conditions. So this is still very general, and of course there are infinitely many such operators. Therefore, in principle, the bare Lagrangian can contain infinitely many terms. And sometimes you can place additional restrictions on which operators can actually appear. And the first kind of restriction comes from power counting. Remember that the theorems that we discussed contain precise information about the power counting degree. Not any operator is necessary to cancel divergences in general, but you know that the divergences can only appear for particular green functions with particular power counting. Therefore, you can learn something about the necessary operators based on power counting rules. But what is the outcome of this analysis depends on the case. And so let me just give you an example here, which is very important. Namely, for example, if the three-level Lagrangian L0 contains only renormalizable interactions of dimension 4 or less, like in the standard model or QED or QCD, then something important holds. So if L0 contains only dimension at most 4 operators, which is equivalent to dimension 0 or bigger coefficients. Okay. So the coefficients are dimensionless, or they are mass parameters or mass square parameters, nothing like 1 over mass. And there is another condition which is often not written out, but let me write it. And the propagators which is equivalent to dimension 0 or bigger coefficients. Okay. So the coefficients are dimensionless, or they are mass parameters or mass square parameters, nothing like 1 over mass. And there is another condition which is often not written out, but let me write it. And the propagators behave as given by dimensional analysis. And let me just give you a counterexample such that you see why that is an important condition. So a counterexample where this is not the case is, for example, the following. Take a vector field propagator in unitary gauge. Then the propagator Feynman rule is minus I divided by p square minus m square times g mu nu minus p nu divided by m square. And then you see the dimensionality is 1 over p square. The unit is 1 over p square, but if p goes to infinity, it doesn't go down like 1 over p square, but it goes like p to the 0 because of this term here. And that violates power counting, and if the theory contains such propagators, then what I am saying does not apply. And that is, however, a rare case, and most of the time in most theories, including gauge theories where you have arc-psi gauges, what I will say is true. Namely, if the Lagrangian contains only dimension 4 or less operators, the divergences appear only for dimension 4 or less operators, and therefore the bare Lagrangian needs only to contain dimension 4 or less operators. So then the same applies to L bare. And then you know that it is sufficient to extend this sum here over all dimension 4 or less operators, and there is typically a finite number of them only. So, and you can do further analyses by power counting, which apply to cases where the Lagrangian contains higher dimensional operators and so on. But let's not do that here. This is just an indication that power counting in general is able to give you interesting relationships. The second condition, which applies to the bare Lagrangian, is symmetries. If the theory contains symmetries, and the symmetries are preserved in the regularization and renormalization procedure, then the bare Lagrangian also contains symmetries, and therefore the operators are restricted by symmetries. Let's just write this down. If L0 has a symmetry which is preserved by the regularization, and we use here specifically dimensional regularization, L bare will reflect the symmetry. And what that means in detail might also depend on the case. It is, of course, quite complicated in the case of Young-Mills theories, but again, this is just an indication. Overall, you can say the following. You can do an a priori analysis based on the definition of your theory, and the a priori analysis will give you some information about which operators can appear in the bare Lagrangian, and you will get some certain set of operators which are possible, and then you know a priori that the bare Lagrangian can be written as some linear combination of operators in this particular set. And if you know this, then you can now infer something about renormalization transformations. So this is basically now an outcome of this line of thought. So often it is a priori clear that you can write or you have written the tree-level Lagrangian as a sum of some coefficients times certain operators, and then these operators are all possible operators of dimension 4 or less, or all operators which have a certain symmetry, and then the bare Lagrangian turns out to be a sum with some other coefficients, but of the same set of operators. So the point is that this sum extends over the same set. And you can do it in both directions. Either you start with a classical Lagrangian, then you do this analysis, and it turns out that the bare Lagrangian requires only operators of exactly the same set. Then you have this statement. Or you do the analysis, you figure out which set is necessary in the bare Lagrangian. You discover, oops, the classical Lagrangian doesn't contain all these operators, so therefore let me modify in hindsight the classical Lagrangian such that I incorporate the missing operators, and then after this both Lagrangians contain the same set of operators just with different coefficients. And if this is the case, then the renormalization transformation recipe works, which is a practical recipe. So we get a practical recipe, namely the bare Lagrangian is obtained from the classical Lagrangian by what is called a renormalization transformation. Which is of the sort fields go to bare fields, which are written as a sketch, some square root of z times the original field. Parameters like gi become bare parameters, which are written as gi plus delta gi, and so on. And let us specify what these terms mean. So there is a standard language associated to this here. So these are called bare quantities. Bare fields or bare parameters. These objects here are renormalized parameters. But at the same time as being renormalized, they are also, by construction, the parameters which appear in the tree-level Lagrangian, or in other words, the classical Lagrangian, so they are also tree-level parameters. They appear in the tree-level Lagrangian. Therefore, as we said, the loop expansion is an expansion in H bar. So these parameters do not contain H bar. They are classical tree-level parameters. And these are renormalization constants. Where the term renormalization constant is actually not a good name. It's called like this, but they are functions of epsilon because they contain 1 over epsilon poles. And also they are regarded as functions of the renormalized parameters. So because they are calculated order by order, and at the lowest order you have this at your disposal, so at the next order this will become a function of the tree-level parameter, and so on. And in perturbation theory, these delta gi, they will be expanded as a power series in the original parameters. Okay, so this is the setup. And this is obviously the practical recipe that you find in many textbooks. And we have clearly seen how it arises from the basic theorems of renormalization. So this is the first point I wanted to mention today. Such renormalization transformations work. There are some tacit conditions under which they work, basically you need to have all operators that are ultimately necessary already in the tree-level Lagrangian. Then it works. If you have forgotten something, then it will not work, but then it's basically your fault, and not the fault of the theory. Good. Let's keep it at this point. Do you have questions to the renormalization transformation?
Well, for this definition of a zero, is this sum specific for Ci not equal zero, or can we have some Ci?
Exactly. So that would be the possibility by which you can save the day. If sometimes an operator really turns out to be not zero at a higher order, but you want to set it to zero at lower orders, because you just want to match to something that you want to achieve, then that is the possibility to write down a parameter which happens to be zero, but it gets a symbol which turns out to be non-zero at higher orders. And then this is just a special case where one of the GIs vanishes, but the delta GI doesn't vanish. And you introduce a symbol, and on the symbolic level, the renormalization transformation applies.
In that case, how does this property even limit our possibilities? How does it help us? Because
well, it doesn't limit our possibility, and that is why you can always achieve that the renormalization transformation works. However, you must be aware of those parameters which you have set to zero. Otherwise, it will fail. So, for example, if, and I think, did I already construct the exercise? If you look at the exercise sheet, problem 2, the last part of problem 2, then this answers exactly your question. Namely, there is an exercise where you have forgotten some term in the classical Lagrangian, and by looking at the divergences, you discover the missing term, and then afterwards you put it back into the original Lagrangian. So that's exactly this case. Other questions? Then let us go to the second point. So the second point is on renormalization conditions. And also known as renormalization schemes. This is basically the same. And what I typically do is I want to simply say, what does it mean to choose a renormalization scheme? And there are many different equivalent ways how you can think about it, and all of these equivalent ways are important. That is why I simply write down all of them. So a renormalization scheme and renormalization conditions are those conditions which fix the finite parts of the renormalization constants, or in the language of last time, they fix the finite parts of the counter-term Lagrangian and the bare Lagrangian. Remember, the main task for us at the moment is to cancel the divergences, but along with it, there is absolutely the possibility to add local Hermitian relativistic finite parts at every order of perturbation theory, and these finite parts become part of the definition of the theory, and they must be chosen somehow. And this is the way they are chosen. So renormalization conditions amount to choosing the finite parts of counterterms and the counterterm Lagrangian. And let me simply say delta GI. And by this I mean all renormalization constants and all counterterms, but let's just formulate everything in terms of this. And when I say choosing it, it means, of course, we work in perturbation theory, and when we choose it as a specific function, maybe a perturbative function, of the actual parameters of the theory. As a function of, and let me again simply say the GI the renormalized parameters.
But that's like a full set. So
Yes. And so there may be mass parameters, coupling constants, whatever. Everything that appears as a parameter can appear here. So this is the basic thing that we want to achieve by choosing the renormalization scheme or the renormalization conditions. And that is equivalent to choosing how we split the bare parameters into renormalized parameters plus renormalization constants. So you might think that initially you start with a bare quantity, you split it into a divergent part and a finite part, but the split is obviously not unique. You can shift around finite parts between the two quantities, and how you shift it around is fixed by the renormalization conditions. If you fix this delta GI in some way, then you can calculate Feynman diagrams, and they are then completely unambiguously defined. So you can calculate even physics. Which formula do you get? This depends on how you have chosen the delta GI. So the scheme choice fixes the formula for physical quantities. And that means we fix the properties of renormalized green functions and functional so you can calculate even physical quantities, observables, and you will get a formula. Which formula do you get? This depends on how you have chosen the delta GI. So the scheme choice fixes the formula for physical quantities. And that means we fix the properties of renormalized green functions and functional form for them. Okay. So whether some
طبعا كما قلنا أن دلتا جي أو الجي عموما تزيد مع الفضاء ثنائي الأبعاد، مع انتصار الفضاء ثنائي الأبعاد أو مع زيادة الفضاء ثنائي الأبعاد، بالتالي لابد أن الدلتا جي يعني تحفظ لنا سيمتري. الدلتا جي تحفظ لنا سيمتري، لكن في نفس الوقت سيكون ضعيفة لأننا نحن نتكلم عن ملاحظ خارجي. الملاحظ الداخلي العكس تماما. الملاحظ الداخلي يرى أن دلتا جي والفضاء ثنائي الأبعاد لا تحفظ السيمتري، كما أن داخل الثقب الأسود نجد أن السيمتري غير محفوظة بالنسبة للملاحظ موجود داخل الثقب الأسود، وإذا رأى خارج الثقب الأسود أيضا يرى أن السيمتري غير محفوظة. لكن من داخل الثقب الأسود هو يرى في داخل الثقب الأسود يرى الأمر طبيعي فيزياء كلاسيكية، يعني السيمتري محفوظة. لكن إذا نظر إلى الخلف أو مثلا في بداية الثقب الأسود ورأى عميقا داخل الثقب الأسود يرى مثل ما نحن يعني نقف في وضعنا نحن ونرى الذرات والجزيئات، نرى هنالك uncertainty، هو أيضا يرى uncertainty عند درجة معينة، لأنه كلما تعمقنا عميقا داخل الثقب الأسود كلما زاد التايم كونتراكشن والسبيس كونتراكشن. حتى لو الفضاء يعني الملاحظ موجود داخل الثقب الأسود لكن على طرف الثقب الأسود، بالتالي إذا نظر داخل الثقب الأسود يرى تايم كونتراكشن، ومع تايم كونتراكشن طبعا تزيد الفضاء ثنائي الأبعاد ويزيد الجي، تزيد الجي إلى تصل مرحلة أنه لا يستطيع رؤية شيء، كما أننا لا نستطيع رؤية شيء في العالم الكمي، وبالتالي يحصل الميجرمنت uncertainty ويحصل كما نرى نحن. هذا كله يعتبر نوع من كسر في التناظرات بسبب التايم كونتراكشن والسبيس كونتراكشن، أو بسبب معدلات تدفق الزمان والمكان العالي.
Observable looks like g square plus g to the fourth, or g square plus 1/2 g to the 4, or g square minus g to the fourth. All of this is possible by choosing the renormalization scheme. So that means what you have also chosen is the relationship between the renormalized quantities and observables. Okay. You have fixed how observables are related to the renormalized parameters. And this in turn means that by choosing the scheme and assuming that the theory actually describes reality, so the observables are fixed by nature. If you fix the functional dependence between observables and the parameters, what it means is you fix also the numerical value of those parameters. So the numerical value will depend on the scheme choice. So all of this is equivalent, and the equivalence means that you should have all of this in mind, and it also means that you can impose the renormalization conditions in different ways. You can, for example, impose a renormalization condition by saying explicitly, my choice is delta gi is a pure 1 over epsilon pole and the finite part is 0. A very direct and simple definition corresponding to the so-called MS bar, minimal subtraction scheme. Then you would use this and everything else would follow. But you could also say the opposite. For example, you might explicitly, my choice is delta gi is a pure 1 over epsilon pole and the finite part is 0. A very direct and simple definition corresponding to the so-called MS bar, minimal subtraction scheme. Then you would use this and everything else would follow. But you could also say the opposite. For example, you might say, I want that the coupling constant alpha has the value 1 over 137 exactly. Then it fixes also how you need to split your G into the bare parameter into renormalization constants. You will get some particular finite part for this as well. And you can do everything in between as well. You might say, I want that my observable is a particular function of the coupling. That is done in the so-called on-shell scheme, where you say that the physical mass of a particle is directly equal to the renormalized mass. M in the theory is the physical mass. Okay, so that is an example of this. Very simple example, extremely important example, obviously. And in general, however, the physical mass is not equal to the mass parameter, but is given by the mass parameter plus some higher order corrections. And so this would be often applied to masses. And therefore, all of these equivalent statements are important and used in practice to set up different renormalization schemes. And by the way, the numerical value is actually important. So for example, have you heard about, I think you have probably heard about MS bar scheme and on-shell renormalization scheme. So one important parameter is the electromagnetic fine structure constant alpha. Just to give you an idea, so alpha in the on-shell scheme has the value 1 over 137 with some decimal places. But there is also an alpha in the MS bar scheme, which then depends on a mass. Let's call alpha MS bar at MZ. And this has a value about 128 with some decimal places. And so you see a 6-7% difference, quite a large difference between the two values. And if you know that typically in QED we measure things up to per mil or a better level, such a 6% difference is obviously very important. So these are differences coming from different choices of the renormalization scheme, and both are important. This has a very simple value for the renormalization constant. And this, on the other hand, has a very simple relationship to observables. So therefore, both schemes have their pros and cons. Similarly, the top mass. There is an on-shell value for the top quark mass, which is really the physical top mass. Does anybody know what is the top quark mass?
I think about 174 gigaelectronvolts.
Very good. So it depends on the exact measurement, but it's about 172 to 174 depending on the experiments. Let's call it 172. But then there would also be an MS bar value of the top mass. Again, this would depend on the energy, let's say m top. And then this is again much different. Here I do not know by heart the value, but it might be something like 163 GeV. So again, quite a dramatic difference. So it is important to know also in communicating results to state which scheme you are working in. And if you look at the measurement tables of experiments, measurement of these masses, for example, measurement of the alphas, of course it is also important for experiments to state which alpha and which top mass they are talking about. All right, any questions to renormalization schemes? Yep.
So even if they have a different numerical values, a physical process will be a different function of this.
That is the point.
Exactly.
That's exactly where the value comes from. And so looking at this here, the functional dependence between alpha and the observable changes. So and also here the functional dependence between the parameter and the measured top mass is different. So in this case, basically the parameter is equal to the measured top mass. Here it is not equal, but there is a calculable function between this quantity and the measured top mass. That's where the value comes from. And then of course you can also calculate the difference in theory. You can predict what the difference has to be. That actually comes next, because now I wanted to discuss scheme changes. And we alluded to this question already the last time, so here I want to give a little bit more detailed answer. So let us discuss scheme changes, such as changes between the different alphas or the different top masses. And here I assume that we are working with a fixed regularization. And concretely, we work in dimensional regularization, and this mu unphysical mass scale is now fixed. That is part of the regularization procedure. Then it is clear from everything that we have said and from the construction that the physical results of anything depend only on the bare Lagrangian. It is not written anymore, but that is clear. The physics depends only on L bare. Because ultimately, we calculate all Feynman diagrams from the Feynman rules in the bare Lagrangian. So if you know the bare Lagrangian, then you know what the final physical results are. And that does not depend on how anybody has split the bare Lagrangian into renormalized plus counterterm Lagrangians, because only the sum ultimately matters for the Feynman rules. And that means that the physics is unchanged if you do, and again let's just do it for a coupling constant G, you have some renormalization scheme 1 plus delta G in this renormalization scheme 1 would give the bare coupling constant, and if that is the same as G in some renormalization scheme 2 plus delta G in renormalization scheme 2. So if the bare quantities in two schemes are the same, then it is a priori clear that the final physical results for everything will also be the same. So it doesn't matter how you split the bare quantities into renormalized and counterterm quantities. What changes, of course, is what is the tree-level part of the calculation. That will be different, but if you sum up all orders, then the difference will vanish. And so that means if you want to relate two schemes, you can simply do this. GRS1 is equal to GRS2 plus delta GRS2 minus delta GRS1. And here you have a relationship which is calculable, because if you know what is the scheme definition in both schemes, then you can calculate the delta G as a function of the original parameters, and you get a calculable relationship between the two renormalized parameters. And this would allow you, for example, to calculate those differences here on the upper blackboard. So this here, that would be in principle a function of GRS2, that would be a function of GRS1, but then you can iterate the equation and write the right-hand side either purely as a function of GRS2 or purely as a function of GRS1. And it is a, let's say, in general power series in either GRS1 or GRS2. By iteration, you can achieve this. So, and then you get ultimately such a formula which I sketched the last time. So the parameter in one scheme are just some function of the parameters in another scheme. And then you have obviously related the two schemes, and it is clear that the physics in the two schemes cannot change. It must remain the same. But what the parameters mean has changed, and the difference is expressed by this formula. So that means the physics is unambiguous. It is fixed by the theory. So relations between observables are fixed by the theory, but different schemes are simply different parametrizations. So this is the important outcome of the discussion. Therefore, the schemes do not amount to changing the physical content of the theory. Therefore, there is just one theory, like there is one QED, but you can use and define QED using different renormalization schemes, which might be convenient for your problem at hand. You can optimize the scheme to what you want to achieve, but it doesn't change the content of QED. And how schemes are related is given in practice by such a relationship. Therefore, as an ultimate conclusion, we can also say something on the free parameters of the theory. So, according to everything we have said, ultimately everything depends on the bare Lagrangian and the bare quantities, but the bare quantities are in any scheme expressed in this way in terms of renormalized quantities plus renormalization constants, and the renormalization constants are functions of the renormalized parameters. Therefore, ultimately everything becomes a function of the renormalized parameters of your theory. And the renormalized parameters are exactly the parameters which appear in the tree-level Lagrangian. Therefore, everything is a function of the parameters of the tree-level Lagrangian. So ultimately, all results are functions. Let's stress finite functions after renormalization of the parameters in L0, the classical Lagrangian. And if the number of these parameters is finite, the theory is predictive. If not, then see you later. So, because in general you would say that a theory must be predictive in the sense that there must be only a finite number of input parameters. That means in practice you measure or do a finite number of experiments. This determines the free parameters of the theory. Then everything is totally fixed, even numerically, so you can afterwards predict an infinite number of new observables and test the theory. If the theory contains an infinite number of free parameters, that doesn't really work so directly, but we will see how in effective field theories, even if we have an infinite number of free parameters formally, we still have some predictive power. Okay, but this is the end of our discussion on renormalization. Let us stop here unless you have questions, and then we turn to the exercise sheet. Okay.